Et tu brute. Tastes good. Okay, so what we've got going on here is another example of Gauss's law, but we're switching it up this time. No more spheres. Okay, what we're going to look at is an infinitely long wire. So a wire that stretches, forever, or as close as forever as we can make. Now, I've drawn here in black my wire. It's going in a straight line like this, and I've made it positively charged. So the wire is positively charged everywhere throughout the wire, even in the center where I can't exactly see it, it's still positively charged. Okay? Now, what we're going to do is we're going to surround this in a Gaussian surface, because we know that if we take that closed path integral of the electric field through some area, through some surface area, that will equal the charge enclosed divided by epsilon naught. Okay. Now what's going to actually happen here when we start looking at this is we can do a little bit of thinking and see the following. If we take a tiny little segment of the area of this sphere, so if I take a little segment of the area of the sphere just like this, I know that its area vector to define the surface of this cylindrical object here, I know it's pointing up like this. That's dA. And I know that my electric field from these positive charges, because it is like a circle, if I kind of take a look, here is my wire and it's going like into the page, the positive charges are out like this. I know that the E field is going to be moving radially out of it. So I know if I have my cylindrical Gaussian shape here, I know that my E field is going to be moving out of it like that. They're going to be next to each other. So picking this cylindrical shape is actually a great idea to match the cylinder which is located inside, which is the wire. Okay, so that surface, that Gaussian surface of a cylinder which is running along the wire, which is a cylinder, is a really great choice to make. So now that our electric field is going to be parallel to that area vector, and that means that when we look at our dot product here, because remember that's a dot product, the cosine term is just going to equal 1, and we can kind of ignore it, which allows us to just quickly take the area of, well, whatever shape we had, which in our case here is this kind of a soup label. Okay. Now, if we go ahead and do this, we need to think of a few things here. First, we know this will be true, our Gauss's law equation, and let's not forget, just a reminder, remember this is equal to an electric flux going through here. But what we need to remember here is that if this entire rod is charged, it's kind of hard to say, like, well, what's the total charge enclosed inside of this? Because, is my Gaussian cylinder, is it a little bit bigger or smaller? Like, what's going on here? So a better way to think about this is to say that the charge that we've enclosed inside this Gaussian cylinder, that's going to be equal to a linear charge density multiplied by some amount of length. And that length is just, however long you've encapsulated. Okay, so however long you have there, that is your length you've got. Now, when we think about our flux, what we're thinking about here is saying, look, I have some flux coming out of the cylinder in all the directions, but that's not the only surfaces I have. I technically also have the bottom and top of this shape. And what's going to happen is if I want that total amount of flux here, that total flux will be the amount of flux going through the top plus the amount of flux going through the bottom plus the amount of flux going through, I'm going to call it like the side, okay? Now, as it turns out, because this is always going radially out with these fluxes here through this wire, I'm never actually going to have anything come through the top or the bottom. They're going to be zeros here, which is really awesome. The only thing I have to worry about is the side, this kind of like wrapping edge of the cylinder. Now, how do we get that? How do we actually figure out what the surface area of the side is? Well, let's take a sheet of paper and kind of map this out. I call this a soup label because what I have here is a little cylinder, right? This cylinder has some length L associated with it. This is the length L here, right? So here, let's take our cylinder and let's do this. I'm going to unroll it. This is length L. if I unroll it, this was L, there's also a length here. Well, what's this length? Well, that length made a circle. What's the length of a circle? Or a better way to say that is, what's the circumference of a circle? When we unroll it, we see that this other edge here is going to be 2 pi r. And if you watch some of the other videos we've done with some of the electric fields, you've seen us kind of take rings and do this, where this is like a 2 pi r and then a dr. Now it's just a 2 pi r and an L. So we've given that other length some value here. Okay, so this right here is the area. That's the area that we have for our cylinder. We've just kind of rolled it up. We've kind of created a soup label. So when we go ahead and set this up, we can see that our electric field, or the flux due to the electric field, just due to our side here, well, that's equal to the closed integral dot dA, where this is this area here. And that's going to equal the charge enclosed divided by epsilon naught. If we start using some of these ideas here, well, this closed path integral here is just going to be the area we had, which is just going to be 2 pi r multiplied by L, because that's just a length times a width, right? You're just saying, hey, look, I've got this and this. That's an area. Boom, we're done. This has to equal, well, what's our charge enclosed? What's that charge on the inside? Well, it was the charge density multiplied by a length, because that's like coulombs per meters times meters. That gave us coulombs. And we divide that by epsilon naught. Now, if we want to solve this for E, we can see that our L's go away, which is awesome. It doesn't matter if you have a very, very long cylinder or a very, very short cylinder. The L's have gone away there. The length of the cylinder doesn't matter. And what we see in the end is that our electric field is going to equal lambda over 2 pi epsilon naught r, which, if we wanted to, we could actually write this in a kind of different way. If I multiply by 1 by saying 2 and 2 here, then I'll get my 4 pi epsilon naught in the denominator, so I could just write that as k. So sometimes you'll also see this written as 2k lambda over r, where 2k and lambda are all constants, and r is the value that will change as you move away from the cylinder. Okay, so as you're moving outside the cylinder, you'll see this fall off as a 1 over r value, which is really, really cool. It is possible to derive this by taking like the actual integral of the E fields, but it's really kind of a pain if you wanted to do that. You have to start using trigonometric substitution in order to do it. Like you could do this for, if you had a charged rod here, and you said, what's the E field out here? You could, take the tiny dq positions, which are, some lambda dl. But when you do that, each tiny position you take has a different r value. These r values change throughout. And the only easy way to do that is with trigonometric substitution. And this is why when we went and we started this AP Physics C, E, and M, when we started finding these electric fields, we did them initially for an arc of charge. Because when we had an arc of charge, all of these r values were the exact same, because this was a circular arc here. If you have it for a line of charge, it's actually doable, but it's hard to do. It's much easier to just use Gauss's law and get an answer like that. Okay, so with that, this Gauss's law for an infinitely long wire is finished. You could expand on this. Right now, we were on the outside of the wire. If you're on the inside of the wire, maybe you have an insulating wire so that you've only encapsulated some of the charges in there. We'll take a look at some of those in the AP Physics free response questions. It's going to be very similar to a solid insulating sphere in doing that, but just slightly different shapes than what we're thinking about as we go through it. But for right now, like I said, this is finished. Adios, everybody, and take it easy.